Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Welcome to section 2.5, Stability in State Space. In this section, I will explain the method to determine stability of a system from the state space equations. Okay, in chapter 1, we have learned how to determine poles and zero from a transfer function. In general, a transfer function is usually written as a division of two polynomials, which are numerator and denominator. The roots of numerator are called zeros, while the roots of the denominator are called poles. The stability of the system is determined from the poles location in the S-plane. There are three system conditions: stable, marginally stable, and unstable. If all poles exist to the left of the half S-plane, then we know the system is stable. A system is said to be marginally stable if the poles lie in the imaginary axis. Okay, when the poles of the system, even if only one pole is located on the right side of the half S-plane, then the system will become unstable. Okay, so now how we are going to determine stability of a system by using the state space method. Remember, in section 2.3, we can easily obtain a transfer function of system from a given state space equation. The transfer function is given by C, Si minus A inverse times B plus D, where C is the output matrix, I identity matrix, A system matrix, B input matrix, and D feed forward matrix. We also know that the inverse of Si minus A is equal to 1 over determinant of Si minus A times adjoint Si minus A. So substitute these values in equation 1, we'll get equation 2. Okay, to make equation 2 in fraction form, we multiply the determinant of Si minus A with the matrix D, and we'll get equation 3. From equation 3, you can see that the upper component of the equation is the numerator, while the lower part of the component is the denominator. Since we determine the stability of a system by looking at the denominator of the transfer function, or actually the root of the transfer function, this value represents the poles of the system. So in general, the poles of a system can be determined from state space by using this equation. Determinant of Si minus A is equal to 0. And finally, after finding the poles, we can easily determine the stability of the system by analyzing the poles location in the S-planes. So now consider this example. In this example, we are given a system with the state equation and output equation as follows. And we need to evaluate the system stability. From the state space representation, we know that the A matrix is 0, 1, negative 9, negative 7. B matrix is 0, 1, and C matrix is 1, 2. And remember that we only need the A matrix or the system matrix to identify the system stability. Note that the state space has two state variables, so the Si matrix will be a 2 by 2 matrix. First, we calculate the value of Si minus A matrix, and we obtain S minus 1, 9, S plus 7. Then, we calculate the determinant of Si minus A matrix and substitute in this equation. We factorize this equation and solve it to obtain S minus -7 and minus 5.3, which represent the pole location in the S-plane. Since both poles are located on the left of the half S-plane, then we can conclude that the system is stable. In the second example, we are given a state space representation with 3 system state variables, and we were asked to determine the system stability. Similar to the previous solution steps, first we determine the A matrix. Then we compute the Si minus A matrix and obtain S minus 1, 0, 0, S minus 1, 0, 36, S plus 15. After that, we find the determinant of this matrix and substitute in this equation. Okay, we factorize this equation and we obtain the value of poles, which are 0, -3 and -12. Since one of the poles is located on the imaginary axis, then the system is marginally stable.